Hello everyone, my name is Christopher Kittrus. Today I'll be talking about ray tracing for graphics. It's a pet hobby of mine. I don't really anticipate being an authoritative source on ray tracing. I do my research in networking, but I hope this is still entertaining and informative nonetheless. So first of all, we're going to jump into the domain specifics of what is ray tracing, how is it done, why is it interesting, etc. But before we can talk about ray tracing, we need to understand what rasterization is. Rasterization is basically just taking an object in 3D space and trying to represent it on a two-dimensional plane. So the idea is we start with, a point of view here, and we go ahead and we project a ray maybe through this grid of pixels, and we superimpose, or we try to superimpose, this shape onto this grid of pixels. So for example, we can see that if this pixel is mainly green from the triangle behind it, we're probably going to turn the pixel green in our image. But maybe in a pixel like this that has barely any green with this low resolution, we won't turn that pixel green, we'll just leave it light. This problem, rasterization, is super quick, it's super efficient, and it's what's known as embarrassingly parallelizable, which means that every pixel can be derived without needing to rely on the information from any other pixels. We can throw this into, a script that uses multiple threads, or maybe use OpenMP or any other tool like that, and this will render incredibly quickly. If we wanted some sort of perspective on our image, some sort of shading, some sort of interesting environmental effects on our image like that, it would have to be in the image we're trying to portray itself. It would have to be artistically added. There's nothing simulated going on in a rasterization. One perfect example of rasterization is the game Doom. You'll notice here in this screenshot of the game, it doesn't look super realistic. All the walls are of the same brightness. Maybe the shading on these barrels are artistic. Maybe this is just the same image flipped over here. We'll notice that this light post really doesn't agree with the shading in this environment, and that the muscles on this monster are also of a different intensity than the ones on the barrels. So it's all artistic. It looks great, but none of it is truly simulated. So if we wanted to actually simulate what an environment looks like in the real world, we have to actually consider how illumination happens. So normally this happens through a light source that emits a bunch of photons everywhere. And these photons bounce off of surfaces at different frequencies, at different intensities, based off, the color and the texture and the reflectiveness of these textures, and ultimately end up in our eyes. And that's what we perceive. But regardless of whether we perceive, these colors or not, maybe I'm looking at this ball, but the sun is also illuminating stuff behind this ball. So from a computational point of view, the real world doesn't really care, how intensive it might be. Everything is illuminated. But if I want to represent this in a computer, I probably don't want to capture and simulate every single ray that the sun or the light in my room is emitting. Rather, what I'll do is I'll start from the perspective of my camera, and I'll draw rays to the light source as efficiently as I can. And you'll notice that this still has kind of the same effect, but in reverse of what the sun does in real life. You'll notice that if I project a ray here at the ground and it tries to get back up to the light source, but it's blocked by this ball, that ray will have to bounce around a little bit before it can ultimately get to my light source. This ray tracing algorithm I have oversimplified because it can get very intense very quickly, but it is still highly parallelizable. Other things that could be added to a ray tracing algorithm based off of this dynamic is, differences in perspective. Things that are closer to the screen will seem bigger than things that are further away from the screen. You can see this in a homemade renderer that I found online right here. The green ball is bigger, not because it is truly bigger, but because it is closer to us. However, if we wanted to get a little more technical and a little more lifelike, we would also have to look at how shadows diffuse over a certain situation. So instead of just looking at the light that is bouncing off of these surfaces, we would also have to consider the normal vectors and the intensity of light that they emit, essentially, which, as you can see in this renderer right here, gives you a nice diffused shadow look. Furthermore, as we talked about before, if we don't have a direct path from our camera to a surface to our point of life because maybe it's blocked by a different object, we can render shadows and how, certain fields won't be illuminated as directly because we have objects blocking those rays. We also have the reflectivity of surfaces. Maybe I have a surface that is so reflective that the light that bounces off of the side of it illuminates another object in the area. You can see that here in this little screenshot of the renderer right here, that this green ball is affecting the coloring of this red ball, because I guess it's so reflective, and the green light waves are mixing with the red light waves and giving this interesting yellow color right here. Finally, we have this idea of, environmental lighting. It's very popular, especially in VFX or just 3D simulations in general, to have a skybox, which gives you some sort of ambient light source, which will give you a little bit more realistic lighting on your scene, as manifested in this screenshot right here. So this is a screenshot of the same game, but with ray tracing turned on, or rather a mod for ray tracing added to the game. And we'll notice that we have appropriate shadows here on the walls and on the floors, and that the lava here is casting a glow on the ceiling, etc. And so, although this doesn't look super real, there are definitely lifelike lighting situations here that make the image look objectively better. If you're not into games and you want to look at Pixar frame before and after ray tracing, here you go. This one that's purely rasterized looks very flat and plasticky, but with simulated real world illumination, everything looks a lot more convincingly real and close to life and intriguing. Now we'll talk about the computational profile of ray tracing and all the stuff that is necessary to make it practical today. So on the Pixar kick, we'll talk about render farms. Maybe you are Pixar and you're trying to render every frame of the most beautiful and provoking film that you can. Instead of taking shortcuts, you probably want to find all of the rays that exist in a specific environment and just throw all the heavy computation that might entail at a render farm. Render farms are just basically thousands of servers and computers all strung together, communicating over protocols like Ethernet or InfiniBand, using technologies like MPI to share the load between different clusters or whatever. From an unofficial source that I found online, I'm not sure Pixar has an official statement on this. Pixar's supercomputer has 2,000 machines, and it has over 24,000 cores. If you do the math, that's 12 cores per machine. I'm not sure if they're counting GPUs or anything like that, but basically 24,000 cores is much better than just one core on one lowly machine trying to do all that ray tracing processing. This is also a look inside of the DreamWorks rendering farm, and you can just tell at the end of the day it's a bunch of server rack mounted machines that are all interconnected with Ethernet cables. Nothing super special. It's the protocols and the organization under hood that really counts. Another way to make ray tracing a little more approachable in a real-time sense is by using algorithmic approximations. I'll admit right now that I'm not the most math-oriented college student right now, but I did find some interesting techniques that people use to approximate ray tracing, because maybe you want to do stuff that's more on the fly, that isn't super important if we have everything that's specifically calculated. And so what we'll try and do is we'll try to use Monte Carlo algorithms or other different modules or algorithms that are added on top or alongside of ray tracing to probabilistically find the most important rays that we actually want to render in our image. So here on the right side of the screen, I have a very simple equation that basically shows you how you should rasterize all the vectors inside of a simulated environment. And then you'll notice that thanks to one of these algorithms over here, we'll add more approximations that will go ahead and exclude the rays that don't actually lead us back to any sort of light source, and take the law of inverse squares into account so that the lighting reflects more lifelike situations. Other things that these algorithms do, which I really have no way to visually show, is that they take into account temporal and spatial locality. So if we rendered something and it was hard fought and we got it in the first frame and it doesn't change much in the next frame, we're probably not going to want to recalculate all of those values and all of those rays, especially if they don't move. So these algorithmic approximations really do help ray tracing become faster, but we still have to recognize that it's not as fast as just raw rasterization, but it is a happy and an exciting new middle ground. Another thing that's used to address ray tracing and make it more fast and more practical is by using specific hardware, like I alluded to a couple slides ago. We would be using GPUs, and GPUs are just, special peripheral devices that have thousands of processors in them to help us do all of the work in parallel that we can. And so inside these processors, we have organized blocks called streaming multiprocessors, which schedule a lot of the heavy lifting. And inside of those streaming multiprocessors, we actually have the processors that do the work. And as we'll see in the next slide, there are specific cores and hardware components that NVIDIA has realized maybe we do ray tracing a lot and we want to have specific hardware that does the ray tracing algorithm, or a lot of it specifically in hardware, which incrementally, boosts the performance of calculating ray tracing. And a lot of this hardware functionality is enabled through SDKs that NVIDIA releases like Optics and Vulkan. For those who are interested in what the inside of a GPU looks like, we have these little rectangles here, which are our streaming multiprocessors, and all these little, you probably can't see the difference between them, but all these streaming multiprocessors are filled up with green squares, which are their own tiny little processors that keep track of the threads inside. But then you'll also notice these yellow squares in here, which are the ray tracing cores, which, in concert with these other regular processors, can do both rasterization and ray tracing at the same time, which is what allows us to have beautiful video games that look very, very lifelike, but also still have the performance of, a rasterized engine. So they do ray tracing where they can and where they want. In conclusion, ray tracing is a very complex and a very exciting topic, and you could spend many hours like I did just falling into all the different math and all the different techniques and optimization styles that exist out there. It's still an open field of research on how to make ray tracing more optimized and more fast. But at the end of the day, all this is meant to serve us. So this helps us with video games, but it also helps us with VR that might exist in the future. It helps us with modeling software. It makes things more capable for us. And so um, I hope you enjoyed this presentation on ray tracing. If you have any questions about it, please let me know. I can recommend some great articles and YouTube videos for you. I hope you enjoyed.